All right, let's talk about thermodynamics today. Okay, as chemists and all biochemists, we need to have fundamental knowledge of thermodynamics. Here, let's review some concepts. The first one, system and the surroundings. System is a part of a universe of interest, such as an organism. Surroundings is the rest of the parts surround a given system in the universe. System has three types. We have three types of systems. Okay, the first one is called open system. In an open system, matter and energy can be exchanged between system and the surroundings. The example for an open system is live organisms, okay, such as the human body. The second type of system is called closed system. Okay, in this system, only energy can be exchanged between system and the surroundings. Okay, matter cannot be exchanged. Okay, example is a sealed metal box. The metal walls can conduct heat. Okay, this is the closed system. The last one is called isolated system. Okay, in isolated system, neither matter nor energy can be exchanged between system and surroundings. The example is a box that is completely insulated, no substance and heat can pass through the box walls. Okay, that's the system and the surroundings. Okay, the second. Let's talk about the energy. Energy, the definition of energy is the capability to work. Okay, the equation defines the energy is delta U equal U final minus U initial equal Q minus W. Okay, in this equation, U is the energy, Q is the heat absorbed by the system from the surroundings, and W is the work done by the system on surroundings. Heat, Q, is the measure of random molecule motion. Okay, the measure of random molecule motion. The work is the quantity of force multiplied by the distance moved by the force. Okay, the energy units are joule and calorie. Okay, next concept that we'll talk about is called state functions. Okay, state functions are the functions only depended on current states, but not the path that a system follows. Okay, energy is a state function and only depends on current properties, such as pressure and temperature. On the other hand, heat and work are not state functions because they are dependent on the path followed by the system in exchanging from one state to another. Therefore, heat and work produced during the change of state are never referred as delta Q and delta W, but rather as just the Q and W. All right. However, changed energy is referred as delta U, okay, because energy is a state function. Okay, now let's take a look at the first law of thermodynamics. Okay, it's energy is conserved. Okay, energy cannot be either created or destroyed. But energy can be transferred between system and its surroundings in form of heat. Okay, two kind of process here. Okay, the first one is called exothermic process. Okay, labeled by minus Q. It's a process the system releases heat. The second process is called endothermic process. It's a plus Q. It's a process the system absorbs heat. Energy can be converted from one form to another. For example, okay, chemical energy can be converted to mechanical energy. Light energy can be converted into a chemical energy such as in photosynthesis. Okay. Now let's take a look at the concept. It's called enthalpy. Enthalpy are defined by this equation: H equals U plus PV. In this equation, H is enthalpy, U is energy, okay, P pressure, and V the volume. Okay, for biological processes, because P and V, pressure and volume, are constant, delta H, okay, the enthalpy change actually is the measured heat that biological system generates or absorbs. Delta H just equal QP. QP is the heat transferred at a constant pressure. Therefore, differences between delta H and delta U, okay, that's enthalpy change and energy change, are insignificant in biological systems. Okay, H is a state function, so the symbol delta H can be used. Okay, let's take a look at a second law of thermodynamics. Okay, the second law of thermodynamics is the universe tends toward maximum disorder. Okay, the universe tends maximum disorder. Okay, let's define some concepts here. A system can be more ordered only at the expense of even more disorder of its surroundings by applying energy to the system. For example, when building a house, the house is ordered state using the materials disordered, energy had to be required. All right. For example, for providing mechanic energy, diesel. Okay, when you run a machine, diesel is ordered substance is converted into carbon dioxide, and water. Okay, the carbon dioxide and water is more disordered than diesel. Okay, and human construction workers had to eat. Okay, had to eat the food, and the nutrients, okay, become carbon dioxide and water. Okay, the nutrients, the food is ordered, and the carbon dioxide, the water is more disordered. Okay, that's why when you when you make a system more ordered, okay, and much more disorders of its surrounding are required by applying the energy from the surroundings to the system. Okay, the disorder is defined. That's the definition of a disorder. Disorder defined as a number of equivalent ways, okay, capital W here, of arranging components of universe. Okay, the term describing disorder is entropy. Entropy is used to measure disorder of a system and defined in this equation: S equal Kb and log W. Okay, S is entropy, Kb is a constant, it's called the Boltzmann constant, and the W is a number of equivalent ways of ranging a system in a particular state. Actually it's just disorder. Okay, like U and H, like energy and entropy S is a state function. Therefore, delta S is used to express a change in S. Okay, entropy disorder of the universe tend toward a maximum. It's the second law of thermodynamics. Okay, in general, for any constant energy process, delta U equals 0, a spontaneous process is characterized by delta S larger than 0. All right. If delta U is 0, and the spontaneous process occurs only when delta S larger than 0. Okay. Next, let's take a look at this Gibbs free energy. Okay, that's the equation G equal H minus Ts. Okay, this is the indicator of spontaneity for constant temperature and pressure. Okay, G is free energy, H is entropy, and S is entropy. Okay, therefore, spontaneity of a process depends on both H and S, both enthalpy and entropy. For biochemical processes with constant T and P, constant temperature and pressure, delta G equal delta H minus T delta S minus equal to QP minus T delta S. All right. When delta G smaller than or equal to 0, delta G smaller than or equal to 0 is a criteria of spontaneity. Okay, that means spontaneous process can occur only when delta G smaller than or equal to 0. That delta G is the free energy change. Okay, in this equation, QP is the heat transferred at a constant pressure. Let's continue talk about spontaneity of the processes. Okay, there are two types of processes in terms of spontaneity. The first one is called exergonic process. Okay, in this process, delta G smaller than 0 is spontaneous. Okay, this process releasing heat. Okay, the heat can be used to work. Okay, the second type is opposite, called the endogonic process. Okay, in this process, delta G larger than 0 is non-spontaneous, driven by the input of free energy. For this type of process, the surroundings have to input energy into the system. At the equilibrium, when the forward and the backward reaction are balanced, okay, those processes are characterized by delta G equal 0, delta G the change of free energy equal 0. Okay, when delta G equal 0, the processes, okay, reach to equilibrium. Okay. Okay, let's take a look at the signs, okay, of the delta H and the delta H and the delta S, okay, to determine the spontaneity. Okay, spontaneity can be described by the sign of delta H and delta S. Okay, the first one, if the delta H has a negative sign, delta S has a positive sign, the reaction is forward in terms of both enthalpy and entropy. It's spontaneous at all temperatures. Okay, at all temperatures. When delta H is minus and delta S is minus, the reaction is enthalpically favored and entropically opposed. It's spontaneous only at a temperature below T equal delta H over delta S. This process, the example for this process is protein folding. Okay, and when delta H has a plus sign, delta S plus sign, the reaction is enthalpically opposed and entropically favored. This is spontaneous only at the temperature above T equal delta H over delta S. Okay, example is protein denaturing. Okay, when the temperature comes to a certain point, okay, the protein become denatured. Okay, the last one is if the delta H is plus, delta S is minus, this reaction is opposed in terms of both enthalpy and entropy. This is unspontaneous in all temperatures. In all temperatures, okay, it's endogonic. All right. The free free energy change represents maximum work, okay, such as the maximum charge separation when breaking a non-ionic bond, or electron separation when breaking covalent bond, or generating a concentration gradient. Okay, next, let's take a look at this chemical equilibrium. Chemical equilibrium is the relationship between free energy and concentration of a substance expressed in this equation. Okay, the relationship between free energy and the concentration of a substance, okay, has this relationship. The Ga bar minus Ga bar degree sign equal RT log A, in square brackets. Okay, this one, the Ga bar, is called the partial molar free energy or chemical potential, okay, of substance A. Okay, the bar here indicate per mole, okay, indicate per mole. Okay, and if we have another label here as a degree sign beside this Ga bar, this indicates partial free energy of A at its standard state. Okay, and this degree sign indicate standard state. Okay, R in this equation is gas constant, T absolute temperature, and A in square brackets is the molar concentration of A. For general reactions, okay, A, B, this reactant, okay, the C and the D are product. Small a is the number of A, and small b is the number of B. Small c is the number of C, small d is the number of D. Okay, the coefficient, okay, indicates the number of molecules. Okay, then we got, okay, this relationship, delta G, okay, the free energy change equal the free energy change at the standard state plus RT log and this concentration term. Okay, the concentration term is on the numerator is the concentration of products, product concentrations. Denominator is reactant concentrations. Okay. Okay. Delta G degree sign is the free energy change of the reaction when all the reactants and products are in the standard states. Okay. The equation indicates that delta G depends on reaction. Okay, the specific reaction. Each reaction has its own delta G at standard state. Okay, and the temperature and all the concentrations of both reactants and products. Okay, from the viewpoint of kinetics, when delta G equals 0, when the free energy is 0, the rate of both process forward and backward. Okay, from the reactants to product is forward, from the product to reactant is backward. Okay, those two processes are equal. Okay, that means a chemical equilibrium is a dynamic but not a static condition. All right, once equilibrium is not static, actually it is both processes still occur. The only thing is that the two rates of both forward reaction and backward reaction has the same rate. That's why they come to the equilibrium. And the equilibrium constant can be calculated. Okay, at the equilibrium, delta G equals 0, so we can get this relationship. Delta G at a standard state equal RT and log K equilibrium. K equilibrium is a constant, equilibrium constant. And after conversion, arrangement, and we can calculate the K equilibrium in this equation, using this equation. And from this equation, we can see that K equilibrium can be calculated using free energy data. Okay, because RT, both R and T are constant. Only variable here is delta G. Delta G at a standard state. All right. Okay. The last thing we want to talk about is biochemical standard data conversion. Okay, in chemistry, all measurements are referred to standard state settings. Okay, it's a relative measurement, which have some differences between physical chemistry and biochemistry. Okay, the standard state of a solute in physical chemistry is set at 25 degrees and 1 atmosphere. 1 atmosphere. Okay, and activity is the unit of standard state. Okay, in biochemistry, activity can be replaced by concentration, because in biological systems, the pressure and the temperature basically are constant. Okay. For convenience and simplicity, biochemical standard state for calculating free energy change is defined as following. We list here have 4 settings. The first setting, activity of pure water is assigned a value of 1 rather than the water concentration 55.5 molar. Water is a standard solvent for biological system. Setting this activity to 1 allows us to neglect the water concentration term when we calculate the free energy change. Okay. The second setting is the pH is assumed to be 7. Okay, since the physiological pH is near neutrality, and a standard state of pH 7 is reasonable. Okay, the third one, the hydrogen activity is assigned to a volume of 1 at pH 7. Okay, at pH 7 rather than at pH 0 in physical chemistry. Okay, setting activity of a proton to 1 allows us neglect the proton concentration term when pH is assumed to be 7. Okay, the last setting is standard state of nonizable substance is defined in terms of total concentration of all the forms, since there are so many ionizable functional groups in biochemical systems. Okay, about the expression. Okay, biochemical standard free energy is defined as delta G, degree sign, and prime. Okay, in comparison with the physical standard free energy, that just delta G degree. Okay, they have the additional symbol prime here. Okay, and the prime indicates indicates the biochemical convention. Okay, the terms in biochemical convention. For example, another example is the biochemical standard equilibrium constant is K equilibrium prime. Okay. That's it. That's all the concepts we like to describe this time about thermodynamics. All right.